Good morning, everyone. Hope you're not too much hungover from that after party last night. Anyway, I'm going to talk about 3 of my favorite things today: JavaScript, Unicode, and 90s gangster rap. But first, I'd like to focus on this tweet that I saw a couple of days ago. Cinderosaurus posted it, and he says, "I don't want to let my cat go outside because I'm afraid he might talk to other cats and find out that their owners don't force them to wear a unicorn horn." And I'm pretty sure Cinder was joking here, because he is joking most of the time. He was not, well, okay, that's fine, but I want to make use of this opportunity to point out that the unicorn horn for cats is a very real thing, and it's not a joking matter. This is what it looks like. This is an inflatable version, so you could just mount it to the top of your favorite feline and play around with it. And as you can see, the packaging says cats love it, so that's all the proof you really need, right? So I ended up buying one of these for my cat as a Christmas present, a couple of months ago. And then this happened. So yeah, as you can see, there was a little bit of a struggle going on there. Like 5 nanoseconds after taking this picture, she was scratching all over my face and stuff. So I'm not sure if love is the right word here, but there was definitely some special kind of bonding moment going on here. So highly recommend it. Anyway, this is me. I'm Mathias. I work for Opera Software in developer relations, and both as part of my job and in my spare time, I like to collaborate on various open source projects. And one example of such a project that I started a couple of years ago is called Unicode.js, which you can see in action here. So basically what Unicode is it takes an internationalized domain name, like the one you see on the left-hand side. This is a domain name that contains non-ASCII characters, like the E with the accent is a special character, And at the DNS level, only ASCII characters are accepted. So if you want this to actually work in a web browser or in any other piece of software that deals with URLs at all, you need to find a way to convert that into a pure ASCII form. And that's exactly what the Unicode algorithm does. So web browsers and other pieces of software that deal with URLs, they all have an implementation of Unicode built in because they want to support these internationalized Unicode-based domain names. So anyway, I found out about this algorithm. It was new to me, and I figured, hey, let's write a JavaScript version of this just for fun. How hard can it be, right? There is this whole document that is basically the RFC for Unicode, and it neatly lists all the steps you need to take in the algorithm. So I figured, hey, I just write code for each of those steps in JavaScript. I basically translate that algorithm, and that's it. It should be fairly simple. But it turns out I was a little bit wrong about that, because JavaScript as a language has some weird and quirky behaviors that I didn't know about at the time, and it made it a little bit harder to implement this correctly. And that's what this talk will be about. But first, does anyone know who this guy is? Douglas Crockford? No. Close, but no cigar. I'm sure everyone knows this is Jay-Z, right? He's a famous American rapper. But a little known fact about him is that at some point he tried to write a JavaScript program once. So he fired up his terminal and started npm installing some dependencies, and then he opened up Emacs, because apparently Jay-Z is an Emacs user, who knew? And then he started hacking away for the rest of the day. But at the end of the day, instead of writing a JavaScript program, it turns out he had written a song about his frustrations with the JavaScript language instead. You may have heard of it before. It's called 99 Problems. Yeah. That guy is awake, yeah. Anyway, even though I'm making fun of JavaScript here, it's absolutely my favorite programming language. I think it's, it's just part of life as a programmer that you're going to be surprised every now and then. And that's also why we have websites like phpwhatthefuck.org, which neatly documents all these weird quirks in the PHP language. And similarly, whatthefuckjs.com, which does the same thing, but for JavaScript. And of course, everything on these websites can perfectly be explained if you just read the specification, or for PHP, you view the documentation, or you read the source code even. But even then, if a particular behavior of a language is confusing to a lot of people, then that becomes a bit of a problem. So I'm going to go ahead and say that I think that JavaScript has a Unicode problem. The way JavaScript handles Unicode is just very surprising, to say the least. And before we get into that, let's talk about Unicode itself. Let's make sure we're all on the same page when it comes to Unicode. So it's easiest to think of Unicode as kind of a database that maps any symbol that you can think of to a unique number for that symbol called its code point, and also to a unique canonical name for that symbol. So this is fairly simple, and it gives you a way to refer to any given symbol without having to use the symbol itself. Because now you can just refer to that number, to that code point, and everyone will know what symbol you will be talking about, because they can go and look it up in the Unicode standard. That's the main idea of Unicode. So for example, Unicode maps the Latin capital letter A to the code point U plus 0041. This is how code points are usually formatted. They're zero padded up to at least 4 hexadecimal digits, and they get the U plus prefix. Now, another example is the Latin small letter A. This is a completely different symbol, so it gets its own canonical name and its own unique code point. I think you start to get the idea now. It's just, each symbol simply gets its own Unicode code point and its own name. And there's a lot of weird characters in Unicode, like there's a snowman symbol, for example. I'm not sure why you would ever need it, but it's there if you want to use it in your text documents. And then if you look at your WebRebels badge, there's the WebRebels logo there, and right next to it there's this hand, this raised fist. Well, it turns out there's a Unicode character for that as well. It's U plus 270A, raised fist, is the canonical name. And then there's everyone's favorite Unicode code point, the pile of poo character, which has the code point 1F4A9. And yes, pile of poo is the actual canonical name in the official Unicode standard. I like to imagine the meeting when this was decided. But anyway, as you can see, the code point is 1F4A9, and I previously mentioned that code points are usually zero padded up to at least 4 hexadecimal digits. But these are 5 hexadecimal digits, so you may be wondering now how many code points are there in total, or what's the highest possible code point value in Unicode? Well, the code point values in Unicode range from 0 to 10FFFF. And these are, of course, hexadecimal digits, so that's a little over 1.1 million possible symbols or code points. Now, I say possible symbols because not all of these code points have been assigned a symbol yet. Most of these haven't been assigned any symbol, and that's because Unicode is forwards compatible. If sometime next week, for example, there is a new currency and someone comes up with a new symbol for that, the Unicode standard can go and just assign that new symbol to any of the unused code points, and then it will automatically start working everywhere. We don't have to come up with a new type of encoding or anything like that. So anyway, this is a lot of code points, and just to keep things a little bit organized, Unicode divides this wide range of code points up into 17 individual planes that consist of about 65,000 code points each. And the first of these planes is called the Basic Multilingual Plane, or the BMP. And it's probably the most important one because it contains all the most commonly used symbols. Now, most of the time, you probably don't even need any symbols outside of the BMP if you're writing a text document in English or Norwegian or German or whatever. So because this basic multilingual plane contains all the most popular symbols, I like to refer to it as the notorious BMP. Maybe that's just me. Anyway, just like any other plane, it consists of about 65,000 symbols. That leaves us about 1 million other code points that live outside of this BMP. And the planes that these code points belong to, they have a group name. They're called the supplementary planes or the astral planes. So similarly, when someone talks about an astral code point, it just means a code point within this range. Now, these astral code points are pretty easy to recognize because you need more than 4 hexadecimal digits to represent the code point. So that's how you know it's an astral code point. Now, that's it. That's our basic introduction to Unicode. Now that we have a basic understanding of it, let's see how this applies to JavaScript. And let's start out by using strings. So you may have seen this sort of thing before. In a string literal, you can have a backslash followed by x, followed by 2 hexadecimal digits. And now that you know about Unicode, it's easy to see what these hexadecimal digits refer to. They refer to a Unicode code point. So again, this gives you a way to use a symbol without actually using the symbol itself. And this is useful in cases when, for example, you have a symbol that is hard to type on your keyboard, or you want to avoid encoding issues when you want to avoid using the raw Unicode character in your source file, because if someone saves the file with a different encoding, it might get mangled or broken. Or if someone misconfigures a web server, it won't send the correct symbol anymore. In that case, you can use these escape sequences like this, for example. This string is basically the copyright symbol, cafe with the E and the accent, and then XYZ. So this is fairly useful in some cases, but in this case, we're limited to just 2 hexadecimal digits at a time. So we can't really use this for a lot of code points. Now, luckily, there's another type of escape sequence called the Unicode escape sequence. And it starts with a backslash followed by U, followed by 4 hexadecimal digits. So this allows us to escape many more code points than was possible before. For example, now we can also escape the code points 2661, which turns out to be the white heart symbol in Unicode. So in other words, now we have 4 hexadecimal digits, so we can use this for the whole basic multilingual plane, all the code points within that plane. But what about all those other planes that we talked about? What about the astral planes? We need more than 4 hexadecimal digits to represent those code points, so how do we do that? Or another way to phrase the question, what about the pile of poo? And other equally important astral symbols, of course. So how can we escape these astral symbols in JavaScript strings if we can only specify up to 4 hexadecimal digits at a time? And the answer is we can actually do this, but it's slightly complicated. In fact, in ECMAScript 6, it will be really easy because it introduces yet another type of escape sequence called the Unicode code point escape. This starts with a backslash followed by U, followed by braces. And between these braces, you can use any number of hexadecimal digits you like. And of course, you only need 6 to be able to represent any Unicode code point at all. So by using this type of escape sequence, you can easily escape any Unicode symbol based on its code point. It couldn't be simpler, really. But if you need something that works today in existing ECMAScript 5 environments, the unfortunate solution is to use this thing called surrogate pairs. Because you cannot represent an astral symbol in just one escape sequence, you need to use 2 separate escape sequences. And each of these escapes represents the code point of 1/2 of the surrogate pair. These 2 escapes are combined together into a single astral symbol. And this is a little bit weird and confusing. For starters, these surrogate code points that you see here, they don't look anything like the original code point 1F4A9 that we're trying to represent. So if you're just reading the code, it's really hard to figure out what symbol you're actually talking about. Now there are formulas that you can use to calculate these surrogates based on a given astral symbol or the other way around. And here's a JavaScript implementation of those formulas. Now, you don't need to remember the exact details here, but apparently you do need to know that this sort of thing exists if you want to deal with strings in JavaScript correctly. Now, anyway, this whole concept of using just a single escape sequence for BMP symbols, but then requiring 2 separate escape sequences for astral symbols is a little bit confusing, and it has lots of annoying consequences throughout the entire JavaScript language. For example, let's say you want to count the number of code points or the number of symbols in a JavaScript string. My first thought would be to just use the length property of the string, right? So if you have the capital letter A in a string and you get its length, it will be 1. And this makes sense because if we use escape sequences for every symbol in that string, and then we count the number of escape sequences, we see that there's only 1 needed there. So it makes sense that the length is 1. In these examples, the length property just happens to reflect the number of characters in the string. But this is not always the case, and that's the first thing that really surprised me. Let's try some other symbols. Here I'm using the mathematical bold capital letter A, which has the code point 1DF400. And now we can see that JavaScript seems to consider this string to have a length of 2 instead of 1, even though there's only a single symbol there, really. And this is because JavaScript exposes each of these 2 halves of the surrogate pair as if they were separate characters, which really they're not. This is essentially an implementation detail, an encoding detail that just bottles up to the developer. So this is very confusing behavior for us as human beings because we generally just think in terms of Unicode symbols or Unicode characters. We don't want to deal with this encoding details. Another example is the pile of poo. If you take the string with the pile of poo and get its length, it will be 2 instead of 1. And for the Americans out there, there's a very obvious joke to be made here. But instead, I'm just going to show you this real-world example of where this behavior actually breaks stuff. I'm sure you're familiar with Twitter. They allow 140 characters in each tweet, and they don't really care what kind of character you use. If it's an astral symbol, it will still count only as a single symbol. It just makes sense. But at some point, they had a bug in their front end. They wouldn't account for these surrogate pairs. And because of that, for every astral symbol you would enter, the counter would decrease in steps of 2 instead of in steps of 1. So because of this bug, it wasn't possible to tweet more than 70 piles of poo at a time. It was truly devastating. Another example is the CountableJester library. Basically what this does is it monitors a text area or an input field somewhere on our page, and then it counts the number of characters, words, paragraphs in there, and it displays those numbers elsewhere on the page. So the first thing I did when I saw this demo page for the project was, of course, to enter a pile of poo. And yeah, then this happened. It counted it as 2 characters. And this is not even surprising, and I'm not naming names here, or I'm not pointing the finger at these libraries or at Twitter at all, because this is really an honest mistake to make. But the bottom line is, if you're writing a JavaScript library, or you're doing anything at all in JavaScript that involves strings, you kind of don't have a choice. You have to make it work with all kinds of symbols in the Unicode standard, not just with BMP symbols, because sooner or later, one of your users will enter such a character, and you don't want your code to break or to start misbehaving in that way. Now, the easiest way to verify that you're doing the right thing and that your code supports these astral symbols as well is just to do what I did. Just throw in some piles of poo and see what happens. Now, entering that pile of poo in there, it kind of felt like this, because I almost knew, I could almost tell that something would likely go wrong, you know? Yeah. So getting back to our problem, how can it be done? How can we accurately count the number of code points in a JavaScript string? Well, one solution is to use a third-party library. And Unicode.js, which I talked about before, has utility methods that it uses internally, and it also exposes them so you can use them separately as well. And it has one called UCS2 decode. It takes a string, and then it returns an array with 1 item for each code point in that string. So if you just get the length of the resulting array rather than getting the length of the string directly, this gives you a more accurate result. But of course, this solution is not exactly ideal, because you just want to count the number of code points in a string, and now suddenly you need a whole library for that. That's surely not what you want. In ECMAScript 6, there is actually a built-in way of solving this problem. You can use the new array.from method and pass in a string there, and that will cause the new string iterator, which is another new ECMAScript 6 feature, to be used. And this string iterator has been defined so that it iterates over whole code points, so it will automatically group these surrogate pairs together and treat them as one single unit. So this will give you exactly the same results without having to use any third-party libraries in ECMAScript 6. Now, another way of solving the same problem in ES6 is by using the spread operator. This is effectively the same thing as what we were doing before. Now, of course, an even more efficient solution would be to use a regular expression to replace all these astral characters with just a single ASCII character, for example, and then just get the length of the resulting string. And that is how Twitter solved the problem. But we'll talk about regular expressions later. Now, I've built this tool, and it takes a string as input, and then it shows you the escape sequences for any special characters within that string. So it's a bit similar to a hex dump, except that the output in this case is always valid JavaScript, which, depending on what you're doing, can be more useful sometimes. So with this tool, it's really easy to tell which Unicode symbols the string contains exactly, even if the symbols are non-printable or just white space. So what I've been talking about so far, about these surrogate pairs and these astral symbols, these are things you have to do for all the code that you write. If you deal with strings in any way, or if you use user input in any way, or you rely on strings that come from a third-party API provider, for example, you don't have a choice. You have to support these things properly, because sooner or later, one of your users will use one of these characters. But depending on your use case and what you're trying to do exactly, there may be even more work that you need to do. For example, in this case, JavaScript seems to be telling us that these 2 strings are different. But visually, there's no way to tell. They look the same to me. So what is going on here? Well, I'll tell you what I did. I took these 2 strings, I copied them into the tool that I just showed you, and this is the output that I got. The first string, as you can see, contains the code point f1, which is the end character with the tilde on top of it. Then the second string has a separate end symbol, followed by the code point 0303, which is a combining tilde character. And Unicode has a lot of these combining marks, and they basically work. They get applied to the previous symbol in the string. That's how they work. So the idea behind these combining marks is that you can use several combining marks for one character, and then basically make all sorts of weird combinations that way. So anyway, this way it's very clear that these two strings are different because technically they contain different code points, different symbols, they have a different length even. So sure, okay, I understand why JavaScript thinks they're different now, but we don't really care about this as a human being. If we want to count the number of code points or symbols in this string, we expect a result of 6 for both cases. So how can we make this happen? Well, ECMAScript 6 to the rescue, it has this new feature called Unicode Normalization. You can just call the normalize method on any string and then pass in the Unicode normalization form that you want to use. I'm using NFC here, and this effectively gets rid of the lookalike symbols that we saw earlier. So if we then account for astral symbols and surrogate pairs just like we did before, we get, yet again, a more accurate result than before. Unicode normalization is already available in Opera and Chrome and V8, but there's also a polyfill. I linked to it at the bottom, so you can already start using this today, and it can work in all browsers. So is this solution absolutely perfect? Well, once again, this really depends on what you're trying to do. For example, imagine a string like this. In this case, I count 9 individual symbols. But the reason this string looks so weird is because there's a lot of combining marks that are getting applied to the same symbols. That's why it looks so messed up. So even our most pedantic function would still count this as 116 individual symbols instead of the 9 that you would expect. So again, this really depends on what you're trying to do, but if you need to support things like this as well, well, the best solution is probably to use a regular expression that strips out these combining marks and then counts the remaining number of characters just like we did before. But we'll talk about regular expressions in a second. Here's another example just to make you think about this problem. Let's say you need to reverse a string in JavaScript. It sounds really simple, right? And in fact, this is a very common solution to the problem. You take a string, you split it up into an array of characters, then you reverse that array, and then you glue it back together. And indeed, ABC gets reversed into CBA. It seems to work fine. Mañana, where the N and the tilde is a single Unicode code point, still gets reversed just like you would expect. But if you try to reverse the other mañana, where the N and the tilde are 2 separate characters, now the tilde suddenly gets applied to the A character instead of to the N, which is probably not what you would expect it. And if you try it on an astral symbol, which, as we now know, consists of 2 surrogate halves as far as JavaScript is concerned, then the reversed result is completely unusable, because you get the same pair of surrogates, but now it's in the wrong order. So this is effectively a form of data loss. You won't even see the original symbol anymore. So even something as seemingly simple as reversing a string becomes really tricky if you need full Unicode support in JavaScript. Luckily for us, a brilliant computer scientist named Missy Elliott came up with a bulletproof algorithm that accounts for these issues. The algorithm goes, I put my thing down, flip it, and reverse it. And indeed, by swapping the position of any combining marks with the symbol that they belong to, as well as reversing and swapping any surrogate pairs in the string before further processing it, like we did before, then these issues are avoided successfully. So thank you, Missy. I actually made a JavaScript implementation of Missy's algorithm. It's called sRever. So if you ever do need to reverse a string in JavaScript, feel free to use it. It handles these cases perfectly. Now, these were just some examples to make you think about the general problem, but really, this sort of problems in the JavaScript language are everywhere. It has these results everywhere. For example, the string.fromCharacter code method allows you to create a string based on a Unicode code point. So you pass in a number, which is the code point, and then it creates a string that contains the symbol that matches that code point. Except it only works for BMP code points. If you pass in an astral code point, it won't throw an error. It will still give you a result, but it won't be the result that you expected. Now, the solution here is to calculate the surrogate halves yourselves, which means you have to implement those formulas that I talked about earlier, and then pass them as separate parameters to this function, which, needless to say, is a pain in the ass. You don't want to be doing this. Now, one other solution is to use a third-party library that implements those formulas for you, so you don't have to do the calculation manually. But again, this is probably not something you want, because now you introduced a dependency just to turn a code point into a string. It should probably not be this hard. And luckily in ES6, it isn't that hard. You can just use string.fromCodePoint, which is essentially just like string.fromCharacter code, except it actually works for any code point, including astral code points. Similarly, the character add method on a string prototype is also affected. So if you use character add to get the first symbol in the string with the pile of poo character, you only get the first surrogate half instead of getting the whole pile of poo character, which is probably not what you would expect. There is no solution for this in ES6 that is built in, but there is a proposal on the table, perhaps for ES7 or ES 2016, as they will probably call it. And it would look like this. You can use the add method, and this would automatically deal with whole symbols instead of surrogate halves whenever possible. Now, character code add has the same problem. If you retrieve the code point of the first symbol in the string, you won't get the code point of the whole pile of poo. You will just get the code point of the first surrogate half, which, again, is probably not what you would expect. But ES6 fixes this by introducing string.prototype.codePointAdd, which does the right thing and combines these surrogate halves together into a single astral code point for you. Now, just another example, just to make you think a little bit more about this sort of issue, is let's say you want to iterate over all the symbols in a string and do something with each individual symbol. In ES5, in current environments, you would need a lot of boilerplate code just to account for these surrogate pairs, because you want to group them together and treat them as one single unit, because they are one single character, really. Now, this is a lot of code, but in ES6, it's much easier. You can just use the new for-off construct, and that will, again, use that string iterator internally, which is defined to deal with whole code points automatically. So this way, you will never run into surrogate halves anymore. It's much, much cleaner and much easier. So anyway, there's a lot of other string methods that I could be talking about, so be really careful when using any of these. And all of this is really unfortunate, but as Tupac would say, that's just the way it is. Some things will never change. Yeah. Now let's talk about regular expressions. You may know that the dot operator in a regular expression matches a single character. But because JavaScript considers astral symbols to be two characters, this surrogate pair, in this case, the dot operator won't match an astral symbol, which is surprising to me. I would expect foo.bar to match foo pile of foo bar, but it doesn't. So let's think about that for a second. If the dot operator doesn't do this, then what regular expression could we use to match any Unicode code point at all? Any ideas? Well, we couldn't use the dot operator itself, as we've demonstrated. Besides, it wouldn't match line breaks either. We can solve the line break problem by using something like this, where we basically match all white space characters and then all non-white space characters as well. This would match any character, but again, because JavaScript considers astral symbols to be two characters instead of one, it still wouldn't work. So, any ideas here? What would the final regular expression look like to match any Unicode code point at all? Yeah, me neither, but apparently it looks like this. Yeah, this is not exactly the type of regular expression you want to be writing by hand, but the first part of it matches any BMP symbol that doesn't start a surrogate pair, and then the second half matches a surrogate pair. And then in JavaScript, it's also possible for surrogate halves to appear on their own in a string, like lone surrogates. Technically, that should never happen, but in JavaScript, it's still valid, so this regular expression would match that too. Now, of course, you wouldn't enjoy writing or maintaining this sort of regular expression by hand, so I used the JavaScript library to generate this for me, and this is how I did it. It's called regenerate, and it has this chaining API that is very easy. So in this case, I instantiate a new set. I just add the whole range of all Unicode code points to the set, and then I call toString at the end, and then it returns a string that I can use as part of a regular expression literal directly. The reason it returns a string is because it's supposed to be used as part of a build script, and then it can directly inject this into your JavaScript source files if you want to do anything like that. Here's a slightly more advanced example, perhaps. So let's say you want to create a set containing all Unicode code points. You want to match all characters, but then you don't want to match the characters in the range from capital letter A to lowercase z, and then you don't want to match the pile of poo. What would that regular expression look like? Well, apparently it looks like this. So once again, I would much rather be writing those 5 lines of code than I would have to write that regular expression manually, let alone maintaining it. Imagine having to remove yet another astral symbol or any other symbol from the matched set for this regular expression. Manually, it would probably take you a very long time to make sure that you're not making any mistakes, but it would be very easy to just tweak the script, and then run it again, and regenerate a new regular expression. Here's another example. So let's say you need a regular expression that matches all the Greek symbols in the Unicode standard, because that's another thing that the Unicode standard does. It categorizes a lot of symbols and code points based on their properties and scripts and blocks and things like that. And there are NPM modules that contain all this data straight from the Unicode database as simple JavaScript arrays, so you can use this as part of your build scripts directly. And in fact, that's what I'm doing here. So in the second line, you can see I'm loading an array containing all the Greek symbols in the Greek script according to Unicode version 6.3.0. And then I'm just passing that array into regenerate and turning it into a regular expression. And that looks like this. So once again, not something you would like to write out by hand. Now, you may have noticed I'm using the data for Unicode version 6.3.0 here, but the latest version is actually version 7. So to update this regular expression, all I need to do now is just change a single line of code in the script like this. So I just change the version number, I run the script again, and just like that, an up-to-date regular expression comes out. So just to summarize this, my advice is if you need complex Unicode-aware regular expressions like this, just write a simple build script using a tool like Regenerate or something else, and don't even try to write any of this manually, let alone maintaining it. It's just crazy. Now, getting back to our problem with the dot operator, we want to make it match all symbols, including the Astral symbols. So the ES6U flag, which is a new flag for regular expressions, magically does this. It makes it match whole code points instead of surrogate halves automatically. So just by adding that U flag to your regular expressions, you automatically make them work more like you would expect them to work in the first place. Here's another example. In character classes, I'm sure you're familiar with this notation where you can say something like A-C, which means you want to match all characters from A to C. And in fact, this matches A, B, and C. I'm sure I'm not telling you anything new here. So similarly, you may expect this regular expression to match the pile of poo, the flexed biceps, and the dizzy symbol, because that's the order these code points are in the Unicode standard, right? Well, it turns out that it doesn't actually work this way in JavaScript. In fact, you get an error as soon as you try to execute the very first line of code. It will tell you the regular expression is invalid, the range is out of order in the character class. So what is going on there? Well, as far as JavaScript is concerned, this is what that regular expression looks like. Remember, these are two Astral symbols, so they are represented by a surrogate pair, and JavaScript considers each half of the surrogate to be a separate character. So now it tries to create a range between the low surrogate for the first Astral symbol and the high surrogate of the second Astral symbol, which is not the range that you tried to create in the first place. And because the first number is greater than the second one, it throws this error as well. So how can we fix this? Well, once again, in ES6, it's really easy. All you need to do is just add that U flag, which stands for Unicode, to your regular expression, and that automatically makes them work like you would expect them to. Ranges will work even if you're using Astral code points. If you need something that works today, however, in existing environments in ES5, you're back to using a tool like Regenerate to generate an equivalent regular expression that works today. And it's good that there is a solution for this kind of problem that we can use, but if you need more than 2 regular expressions in your project, you probably don't want to start writing a separate script for each of those regular expressions. It becomes a lot of work, and your source code won't be really readable. Instead, it would be much better if we could just pretend to live in the future and write our code in ES6, use that new U flag, even though it doesn't work anywhere yet today, and then at build time, convert those regular expressions automatically to equivalent regular expressions without U flag, just like we're doing here, but manually. And that's exactly what I built. I created RegExBoo, which is essentially a transpiler for JavaScript regular expressions. So that use the U flag in ES6. So we can feed it any JavaScript file, it will parse it, it will find regular expressions within it that use the U flag, and then it will rewrite those regular expressions to equivalent regular expressions without the U flag that work today. And here's an example of that. As you can see, it can transpile things on the fly and then run it in existing browsers, in the browsers of today. Now, if you're already using ES6 in your projects, you're probably using a transpiler like Tracer or Babel, And in that case, there's some good news, because both these transpilers already use RegExBoo internally to rewrite regular expressions that make use of the U-flag. And this means that you can already start using this today. You can write your regular expressions with the U-flag and stop worrying about all these Unicode issues and just have the transpiler deal with it for you. Okay, so I think it's fair to say in summary that JavaScript has a bit of a Unicode problem, but rather than complaining about it like Jay-Z did, we should be doing more of this instead. Yep, we should just deal with it and work around these issues, because it's really not that hard once you know how. And I think the problem is not that developers don't want to fix these issues. I think the problem is that a lot of people just don't know about them, just like I didn't know about them. So it's mostly an awareness problem, and one thing we can all do here today to help out with that is just to apply the pile of poo test vigorously. As soon as you write some JavaScript code that deals with strings or regular expressions in any way, all you need to do is just add a single pile of poo to your unit tests and see if anything breaks. That's a good way to make sure you're doing the right thing and supporting Astral symbols correctly. Also, if you're using a third-party library, why not submit a pull request with a pile of poo in it? Add it to the unit tests, and I think if we all did that today, I'm pretty sure we would collectively discover lots of bugs. And of course, discovering bugs is the first step into getting these problems resolved. So go forth and spread piles of poo. Thanks.
That was a great talk. Would you like to come join me in the lounge?
Of course.
So I think we all sort of thought that that was going to be a very heavy technical talk first thing in the morning, but you made something very heavy and technical being really, really fun. So thank you for that.
Thank you. That's what I was going for.
Excellent. So were you sort of saying that ECMAScript 6 fixes all of our problems in the future?
In a way, and in fact, this is a question I get asked very often. Why doesn't ECMAScript 6 just fix all the weird behaviors in the first place? Why does it add new APIs instead of just fixing the existing ones? And the problem is that if we were to change the existing behavior, a lot of existing code on the web would just break because it relies on that broken behavior. So that's why there's a lot of new methods being introduced that seem to do almost the same thing as the existing functions, but they now support all kinds of Unicode symbols instead.
Yeah. So are there any sort of ECMAScript 5 to 6 compilers that allows that support in generated code?
You mean ECMAScript 6 to 5 transpilers? Or?
6 to 5, yes.
Yeah, yeah. Yes, like the two I mentioned, Tracer and Babel, they are able to do this. So you can, all the features I talked about, you can just use this today in your source code, and then you just need a build step that automatically transpiles it using one of these tools into code that works in existing browsers today. So I highly recommend doing this, not just for these features, but for all the other ES6 and even ES7 features that are already available in these transpilers.
Yeah. It's a good idea. I noticed that you managed to tweet on your way from the stage to the couch. Well
Yep.
done.
I'm smooth like that.
Yeah, so all his slides and notes are up on the web. Now I want to ask you one question about your presentation. What tool did you use to capture like all the little animations that you have of trying out the tools? And
That's just QuickTime, and I do a screen recording. Yeah, I'm kind of scared of live demos. Like the last presentation yesterday was an actual live demo. He wasn't faking it, and I was like, oh my God, this guy is insane. I could never do that because there's just so many things that can go wrong. So instead of live demoing stuff, I mostly just record my screen in a safe environment at home. And yeah, it works.
that's good. And I'm also quite happy to see the return of the animated GIF in your presentation, because really there hasn't been a lot of animated GIFs this year.
Yeah, you're welcome.
Thank you. Thanks, Mathias.
Okay, thanks.